Okay, so welcome everybody to round 2 of the Algebra, Particles, and Quantum Theory seminar series. I'm grateful that we are able to open this series with tonight's speaker, Denjoe O'Connor. Denjoe is currently director of the School of Theoretical Physics at the Dublin Institute of Advanced Studies, or DIAS for short. He has quite a wide range of research interests, including particle theory, statistical physics, M-theory, gauge gravity duality, topological insulators and spin systems, matrix models and emergent gravity, causal set, quantum gravity, and non-commutative geometry. On the topic of non-commutative geometry, Denjoe will be telling us tonight about a paper he wrote together with Brian Dolan entitled Exceptional Fuzzy Spaces and Octonions. Now, before we begin, I would like to emphasize that everybody who showed up here today is here to learn. And so I hope that everyone feels comfortable enough to raise their hand and ask a question throughout the talk if they have one. If you accidentally ask a silly question, it is not a big deal. You just brush yourself off and try again next time. I would especially like to encourage questions from graduate students, upper level undergraduates, and postdocs. So Denjoe, anytime you're ready.
So
there we go. Now you're muted. Sorry, you were muted. It looked like for some reason. Now you're ready to go.
Okay, sorry. Well, thank you all for coming. I recognize lots of friends in the audience, and thanks, Nicole, for the opportunity to present this material. I wasn't quite sure what audience I would get, so I filled this with a lot of background, and we'll get to the details of this at closer towards the end, probably. It depends on how patient you are. But I gave you an abstract which I can skip ahead from. So basically the outline, it's very brief sketch of the outline is I wanted to introduce the subject to you, tell you in some detail about the fuzzy sphere because it's the simplest example. And then I was going to describe relatively briefly a fuzzy S4, and then I will tell you about the results on, or some of the results on this this paper that Cohl referred to. Right. So, first of all, many of you probably are already very familiar with non-commutative geometry, but I thought I'd just give a brief few words on the perspective in contrast to ordinary Riemannian geometry. Riemannian geometry, one normally thinks of specifying a metric, and I've written down the metric here for S2, just the line element, ds squared is with a radius of the sphere R, and it's just ds squared sine squared d phi squared. Very familiar, and in generalizations of that are just G mu nu. And one goes into all of local differential geometry, Riemannian geometry, Einstein gravity, etc. But an alternative approach to geometry is that motivated by which I think its origins are probably in Weyl's law. Weyl's law tells us that if I take the Laplacian and I count the number of eigenvalues of the Laplacian on any manifold on any d-dimensional manifold, asymptotically for large number of eigenvalues, the number of eigenvalues less than the cutoff grows as the dimension, grows as the cutoff to the d, with some universal coefficients, which are omega d and the volume of the unit ball in Rd divided by 2 pi to the d. If the manifold has no boundary, the next term up is associated with the scalar curvature, the scalar Riemannian curvature. The next terms after that are R to the 4th type terms, and it depends in detail on whether there are other connections and that. So Mark Katz, I didn't put the reference here, I should have. It's in the 1950s, asked the question, can you hear the shape of a drum? And he was motivated by by this extension and the fact that the leading terms were the curvature, etc. And the answer, well, he didn't answer the question in his paper. He just gave some classic examples of where it looks like you can hear the shape of the drum. And his question was, I'm only allowing you the spectrum of the Laplacian, and from the spectrum of the Laplacian, can you reconstruct the manifold? A little bit, about 10 years later, Milner came back and with a counterexample in 16 dimensions. He wrote down a rather nice counterexample, which was to take the 16 torus, S1 to the 16, and that has an identical spectrum for the Laplacian, but there are two geometries there. One is associated with the 8 cross E8, and the other one is the torus of SO16. So the answer was no, you can't in general. But Alan Kahn and his and I think it was more also a T, motivated by a T, and the index of the Dirac operator on manifolds provided a method of, in reality, reconstructing the geometry from the spectrum, but the spectrum of the Dirac operator. So he can give the geometry in terms of a spectral triple. So for this, you needed an algebra, the Hilbert space, and a Dirac operator. And the algebra, so with this spectral triple, one can, then, and there are various different refinements on this, which I don't want to get into, and I don't particularly want to go into the non-commutative geometry so much of this. There are other experts who could do it much better than I could. So, but I want to give you an idea more of of what is involved. So, for instance, if I just take the ordinary two-sphere, and I want to concentrate a little bit on this example, the ordinary two-sphere S2, I can give you the algebra of functions on S2. It's just the algebra of the YLMs, the spherical harmonics. You can take spherical harmonics, multiply them. You will get a closed algebra in terms of spherical harmonics, and they are generated by xi, which is the unit vector in R3. The unit vector in R3 is equivalent to y1m. So y1m generates the spherical harmonics. You multiply them, you get xi, reduce it by invariance. Xi is the square. And this you can visualize as a nice sphere embedded in 3 dimensions. If I take the Dirac operator on the sphere, the Dirac operator D on the sphere can be written as sigma dot L plus 1 over R. And this form was emphasized by Balachandran and collaborators. It's a nice form. The spin connection is kind of hidden in here, but if one checks, one can see that this reproduces the exact spectrum of the Dirac operator on the round S2, and L is just the generator of rotations, and epsilon is the epsilon tensor, and H is the Hilbert space of the Dirac operator. And from this data, one can reconstruct the two-sphere in detail. And many people have gone into that in some detail. The Laplacian on the two-sphere is then normally you write it in differential geometry as d star d, or perhaps I should have written star d is equal to L squared over R squared, and its spectrum is L times L plus 1 over R squared with degeneracy 2L plus 1. I'll concentrate on the Laplacian because it's easier to describe the details. But in these spaces, you can generalize to a Dirac operator. The Dirac operator is often much more complicated to describe. One of the nice developments in this subject was by John Madore and in his Classical and Quantum Gravity paper in 1992, he made this rather simple observation that one can write a non-commutative version of the sphere. And though the quantized sphere existed prior to that in the work of Berezin, for instance, in his Berezin quantization, Mador introduced the geometry on this manifold, on this space, non-commutative space. For instance, in the simplest observation is just to take the Pauli matrices, I've called them tau I here, to distinguish them from the sigma I, because they're meant to live in different spaces. The tau I is 3, the sum of the squares, and this is 3 times the identity matrix. So looks like it's describing a sphere of radius square root of 3. The algebra, if I keep multiplying and forming an algebra from the tau I, you can quickly see that it's going to be a complete matrix algebra, and it just gives you mat2, the matrices, all 2 by 2 matrices. So this matrix algebra is spanned by the Pauli matrices and the identity. The Dirac operator on this space is sigma dot tau plus 1 over square root of 3. And this has a rather asymmetric structure, but it functions as a Dirac operator. Not quite ideal for a spectral triple. John Barrett has improved on that, and I would recommend his work for if you want to really get into the spectral triple aspect of it. But the Laplacian is what I want to focus on, because just to a large extent, once you understand what's happening with the Laplacian, you can just do more work and work with the Dirac operator. So the Laplacian on this space, our d star d, is the commutator of tau with our matrices, which behave as functions. And I put in the 3 to give it on this sphere of radius 3. And the spectrum is cut off at, it has L equals 0 and L equals 1. Just more general representation is to take an n by n irreducible representation. Take the generators Ji of SU2, and I've written Ji is J times J plus 1 times, again, there's a unit matrix here, a unit n by n matrix, and since J is n minus 1 over 2 in that representation, n by n representation, you have J can be written as n squared minus 1 over 4, and this is the quadratic Casimir. And if I now take xi to be ji over the square root of C2n, square root of this Casimir, you will get, this should be in a capital X, this xi being the identity matrix. However, now it's non-commutative. We have xi, xj is I over the square root of C2n, epsilon ijk xk. And you see that square root of C2n goes like 1 over n. So as n goes to infinity, you recover a commutative sphere, xi, with the x's commuting. The xi's, well, they provide non-commutative versions of the spherical harmonics. They correspond to YL1. And one can generate the algebra again by taking products of the xi's to form a closed algebra, and it closes to the algebra being mat n. If I take and defining Li, my rotation operator, as being Ji, the commutator acting on an element of my algebra, then you can again define a Dirac operator, D on this space, D on, now this would be on spinors, there's 2 copies of them, as being sigma with the commutator of j dot I plus 1. And the Laplacian, again, is just this quadratic Casimir, j into j plus 1. But now it's a reducible representation, and you can easily check that the spectrum is cut off at L is equal to, that's a typo, L should be equal to 2n, I believe. Yeah, sorry. Yeah, I have it written correctly here. We can understand the cutoff in the spectrum from the addition of angular momentum. If you think of mat n as a vector space of dimension n on the left, and note that, where am I? I'm going to take j acting on the left minus j acting on the right. So this, our Laplacian here, is acting as the commutator, and this commutator satisfies the SU2 algebra as well. So we can think of it as, oops, where am I going? We can think of the of this as the left action, the left Hilbert space Hn tensored by the right Hilbert space Hn. And if you add the angular momentum, these are each of angular momentum n minus 1 over 2 times n minus 1 over 2. You can sum. I have labeled them here by the dimension of the Hilbert space, by n is equal to 2l plus 1. So we take n cos Hn is a sum from n equals 0 up to 2n, h little n, where little n is 2l plus 1. And this is just an ordinary addition of angular momentum. And this provides the decomposition. If I take the symmetric, if I symmetrize the xi as xi xj minus the trace part, that would be the n equals 2. N equals 1 is the identity. N equals 2 is L equals 1. N equals true. Yeah. N equals 3 is L equals 1. Sorry. These are the odd ones. I have a typo here as well. We have the we can map the xi onto the commutative algebra xi onto the xi, these matrices, and we can map any function. We can think that it being mapped, the function f is mapped to some matrix, and 1 over n, omega is the volume form, and the integral of 1 should give us 1, where I have normalized omega to be volume form over 2 pi, over 4 pi, sorry. And I have 1 over n times the trace of the identity being 1. So this is the normalization. And the Laplacian is being mapped to this double commutator. And the product of two functions, well, one can pull it back from the product of matrices to a star product. And this allows some tools for analyzing the large n limit. In more detail, if I take a function and an ordinary function on S2 and I expand it in terms of spherical harmonics, I can consider a particularly special matrix, which is rho n. It's built from pairing the spherical harmonic with its polarization tensor of the same spherical harmonic labels. But now this is a matrix which is built from the x's in a particular way. And there are different constructions which give this in a relatively efficient fashion. This matrix here, if I take the integral of any function against this matrix, rho, it'll give me a matrix. And what it'll do is it will remove the YLM from the function and replace it by one of my y hat LMs. and give me a matrix which has exactly the same coefficients, my FLM will be unchanged in the matrix F. So this is a truncated version of the functions on the sphere. You can go back, but not completely, because we have projected out spherical harmonics that are larger than the cutoff. They're sent to 0, but we can go back and recover the cutoff function as 1 over n times the trace of rho n Fn. And you can, using this rho, you can develop the star product from that. It's a slightly different star product to the one that you get by, there's an alternative version of this which is built from coherent states, and you get a slightly different star product. It differs in that the leading symmetric term is 0. So Fn it now represents this function with angular momentum greater than the cutoff projected out. Okay. So we can discuss, once one has a geometry for the sphere, one can think of, well, could I do field theory on the sphere? One can, and the simplest case is to consider a scalar field. If I consider a scalar field, just phi, it's now should be represented by a Hermitian matrix on S2F. So a simple Hermitian matrix, and which is an element of my Hermitian element of my mat n. And if I consider the action, just simplest model, interacting model that one can consider is the Euclidean action for a phi-4 theory. Now on a scalar field, it will give S of phi being the trace of A with my Laplacian, phi squared and phi to the 4th. And I've put in arbitrary coefficients A, B, and C, because a priori, if I'm going to deal with this as a classical problem where I want this functional to be an approximation to the functional, that the continuum functional, where I map my phi from the function, the commutative function on the sphere, I can do that, and I can show that with A being 1 over 4 pi and B being appropriately chosen, and C, I didn't write them down here, what the numbers are there, but one can easily work them out. The limit of the modulus of S minus S, the integral with phi to the 4, that limit goes to 0. But if I quantize the system by Euclidean path integrals, for instance, I don't know that these coefficients will stay the same, so I've left them arbitrary. This would be the type of thing one would do on a lattice problem. If one put the phi-4 theory on a lattice, you'd say, well, let me put in arbitrary parameters here, and I will then try and find the continuum limit by going to an appropriate critical point for the model. And you would look for some scaling of the phase diagram, which stabilized the transition curves and their dependence on n. It turns out that one can do exactly the same in the fuzzy sphere, that one can stabilize the transition curves by scaling A tilde to 1. There's no loss of generality in rescaling A tilde to A tilde being 1, because I have an arbitrary scale associated with phi, and if I'm integrating out phi, it just disappears in the measure. And B tilde as B over A squared n squared into the 3 halves, and C being C over A squared n squared. It stabilizes the transition, and one can do numerical simulations. It turns out that the phase diagram is not really the same as the phase diagram for the commutative problem. If I did it on the lattice, I would get just one transition line, I would just get 2 phases. I would get a uniformly ordered phase and a disordered phase. The uniformly ordered phase, the usual way of thinking of phi-4 theory in 2 dimensions is that it is a massive deformation of the two-dimensional Ising model. It's very closely related, and if I go close enough to the critical point, it becomes the Ising model, two-dimensional Ising model. And the two-dimensional Ising model in this setting should only have one transition, whereas this 5-4 theory has two. It has a transition from a uniform to a non-uniform, and it has a transition from a non-uniform to a disordered phase. The disordered phase looks a lot like the high temperature Ising phase, and the uniformly ordered phase looks a lot like the low temperature Ising phase, but the non-uniform ordered phase looks quite different. And the existence of this is not overly surprising, because when you have cut off this theory, you have introduced in the star product way of thinking of it, you've introduced higher derivative terms, and they can give some new effects. And we in this paper this was with Samuel Kovacic, we localized the triple point. The three phase lines meet at a triple point, and we localized it to this blue region. So that an alternative point of view on the fuzzy sphere is, well, you could imagine that maybe I can find it in some dynamical setting. There's a very nice little model where this actually happens, and I'm just going to take a couple of minutes to describe this to you. If I take this action functional, S of x being -1/4x, the commutators of the x's, with an epsilon tensor, it's not difficult to show yourself that that the ground state of this functional is, and the minimum, the absolute minimum of it, is XA as being LA, where LA is the generator of SU2 in the n-dimensional representation, and these are n by n matrices. So that's the largest dimensional representation. The commutator here, you see the commutator will give us an epsilon times an L. If I square it again, I will get two epsilons contracted with two L's, but that two epsilons are going to give us a Casimir of SU2. They did give us a 2 essentially, and the L squared is going to give us an L squared back. Again, this here has a commutator. We'll get an L square, an L from this contracted with another L, and this will give us L squared. And the two of them compete. This one is positive, this one is negative. The overall result is actually negative for this particular action, and the minimum is L, and it goes to -infinity when you take the large n limit. But one can put this little model in a thermal bath, put in a beta in front of it, and it turns out that this system undergoes a phase transition at beta is equal to 8/3. And at low temperatures, this fuzzy sphere configuration is the ground state, but at high temperatures, there is no geometry. So this is a rather nice model for a geometry. This is a paper I wrote with Rodrigo Delgadillo and Badis Yidri, where we looked numerically and analytically at the phase transition, and you can track down precisely what the nature of the phase transition is. It's got a divergent specific heat. It's got the fuzzy sphere phase at low temperature, and this was with a mass deformation. But it has the alpha here represents the temperature. It's the 1/4 power of it. I'm not sure why we changed this to 1/4 power. But that's this is the so beta being small is high temperature. This is the high temperature phase. This is the low temperature phase, and you can see that as you cool the system down, it condenses into a fuzzy sphere, or as you heat it up, it bursts. Your fuzzy sphere bursts. So this was a nice model of emergent geometry, and in general, I think you can do this type of thing with many of these models. Another place where fuzzy spheres naturally enter is in the BMN model. I've written down the Euclidean action for the BMN model at finite temperature. It's again just a matrix model, and these are n by n matrices. Now there are 9 of them, I and j going to 1 to 9, and it's supersymmetric with fermions. But you will notice here these X, R, S. This is essentially or is very close to the -1. Yeah, no, sorry, it's okay. This is very close to the model that I showed you before. If I expand it out, the first term is the same, the second term is the same, but there is a mass, an m squared, a mu squared term, x squared, so that the ground state of this one is always positive. But there's more structure here. And if you analyze this one in detail, you actually can see that at low, as the temperature is reduced, fuzzy spheres start jumping out. They get excited. And these ones here are correspond to different size representations of fuzzy spheres. So it has the fuzzy spheres are fluctuating in this setting. Okay, so that's more or less what I wanted to say about fuzzy spheres in two-dimensional geometry. I want to now think, can one go further? We started with 2x2 matrices and the poly matrices. The next natural generalization would be, well, let's try doing the same game with gamma mu. I should have asked, are there any questions there? People are completely silent in the background, so hopefully there are people still there. Hello?
Any questions?
Oh, yes, I was. I heard of someone giving a complete lecture who discovered that their Wi-Fi was down, and no one responding. So I thought, but I heard nothing there. Maybe everyone had gone, and I should go home.
No. I've
Okay.
got some more questions for you, but they're going to probably be more related to octonions. So I think
Yeah, no, that's fine. Yeah, it's.
I'm also waiting for the G2 case.
Okay, it will be in a minute. Yeah.
Okay.
Yes, G2. Yeah, we'll get to that in a minute. But so S3 and S4. Well, one could try playing the same game with gamma matrices, and gamma matrices are 4x4 Hermitian matrices, Euclidean. And so if we take the sum of the gamma mu, we get 4 times the identity, and this looks like a tree sphere. But the problem is that the algebra of the gamma matrices doesn't close on the gamma matrices. So in contrast to the poly matrices, it closed on the poly matrices, and when you took symmetric tensor products of those, it also closed on the poly, on their and the L's, so we didn't need to introduce something new. Whereas now we need to introduce, it doesn't close that. What the 4x4 matrices, if we keep multiplying them and forming an algebra from them, we get mat4. And mat4 has 15 generators plus the identity, so that's our 4x4 matrices. And the complete basis would be gamma mu, gamma 5, sigma mu nu, and gamma mu times gamma 5. So we have 4, 5, 5 is 6 is 11, and 4 is 15, plus the identity. However, one can take the next step and say, well, let me take the gamma A. A is 1 to 5. Maybe that gives me an S4. Again, that's going to close on mat4, but if you think of the 15 elements, the 15 gamma matrices and the 10 generators, well, I can form them into spin 5 or spin 6. Spin 6 is the same as SU2, or SU, can I say, is the same as SU4, and one can form a fuzzy version in a very similar fashion to what I described for CPU for S2, which is CP1, and one gets a fuzzy version of CP3. But CP3, if you look through the details of how one has constructed it in terms of gamma matrices and the sigma AB that are the generators of spin 5, you can see rather easily that it is a bundle over S4, base S4, and a CP1 bundle over S4, and this is essentially used in twistor space. And so I've given you, I've written it out here as spin 6 or over U3, which is spin 6 is the same as sorry, it should have been U3 cross U1. I left out U1 there. Or SU3 cross U1, sorry, is what I should have written there. But the middle one is sloppy. There's lots of typos, I'm really sorry. But it is spin 5 over SU2 cross U1. One of the points is that if I write it in terms of spin 5 over SU2 cross U1, you can see that you can put a different radius on the CP1 than on the S4. So you can make the CP1 a tiny little fuzzy S2 sitting over S4. And this construction is of course, in the commutative case, is very well known. And Harald Steinecker uses this and interprets the additional modes as part of his higher spin gravity, which is built over S4. And what the other comment is that S4 is not a complex space, and CP1 is essentially the bundle of what wants to be complex structures on S4. So one can generalize it even further, or one can form a general matrix version and go to the commutative limit by taking L copies of this fundamental of SU, this in our case it was SU4, or with its anti-fundamental, L copies of that. This will give us an L times a DL times DL, where DL is the dimension of this Young tableau, dimensional representation. If you expand it out, multiply these out, you will get an expansion in terms of the Young diagrams, which you can see corresponds to the polarization tensors or the eigenfunctions of the Laplacian on CPN. So one can generalize the construction, and it has been done to more general cojoint orbits of supergroups and flag manifolds, many of these ones. And I'd give you a reference here to some of that work. My student, Sean Murray, and postdoc Christian Seaman developed that. So if I don't go on to this infinite family of spaces, the next simplest thing one might consider would be G2. So we're on to G2. And let me ask if there were questions before I start on G2.
Questions?
Yeah.
No, might as well.
Okay. All right. So let's continue on to G2. G2 is a 14-dimensional exceptional group. Its Dinkin diagram is not symmetric, so it has only real representations. I've put a dot and a black dot, a white dot and a black dot, to represent the two nodes of G2. Its smallest representation is the 7. I'm describing representations by their dimension, the 7-dimensional representation. And it has 14 real 7-dimensional generators. And the quadratic Casimir, if I take those ones and minus 1/4, sum of those generators on this 14-dimensional space, or this 7-dimensional representation, we have the sum being 2 as the quadratic Casimir, and I've written I as the 7 by 7 identity matrix. But 7 times 7, a general matrix, again by TAs, if I was to use those to fill out an algebra, we would get a 49-dimension or a 7-dimensional matrix, which has 49 components. One can split that up under G2 as 7 by 7 is 49, so it splits as the identity. It's another 7. A 14, the 14 is the adjoint representation, which we've described up here, and the 27-dimensional representation. The 7 and the 14 are the antisymmetric 7 by 7 matrices, and the 27 are the symmetric 7 by 7 matrices. So we 49 matrices, the identity and the 27 give us our 28 symmetric matrices, and we have 21 antisymmetric matrices.
Did you just start with the 7 by 7 because it's the simplest thing?
I started with the 7 by 7 because it's the simplest thing, and it's the natural analog of the Pauli matrices for G2. They're the smallest dimensional representation, and we can begin with that to try and understand what's going on.
Okay.
Right. But it has some nice structure as well. Just say a few words about the general representations of G2. Since there were just 2 points in the Dinkin diagram, we just need 2 Dinkin labels, which makes life a lot easier if I only have 2 labels to describe all representations. So we can describe all representations by in1 and in2. And the 7 is our 1, 0. The 14 is our 0, 1, and the 27 is the 2, 0. And in fact, this is the dimension. I've written out the dimension of all those representations, and I've written out the quadratic Casimir just for completeness. And one other observation is that if I take n1, 0 here, it is a symmetrized version of the 7. So we're symmetrizing the 7 into n1, 0. And that will play a role as we go along. Now, it's known that there are 3 non-trivial coadjoint orbits of G2, and in fact, using the construction and the language that I am using here, one can understand all of these rather easily. I won't take you through all of them because that'd be a hell of a lot of detail to go through in one seminar. So I'm just going to focus mainly on the middle one here, which is G2 mod U2 minus. The thing is that there are 2 U2s because the 2 nodes in the Dinkin diagram are not equivalent. So I'm labeling one of them as G2 mod U2 minus and the other one as G2 mod U2 plus, and they are actually quite distinct spaces. And they reflect the 2 ways of embedding U2 into this. And I didn't say it in any detail, but in fact, that fuzzy construction that I described, one can extend it to essentially all coadjoint orbits of all the classical groups and their supergroups. So we should be able to consider, we should be able to go through the construction here in this case. And that's what the task is to understand how those representations fit together and how they and what geometry they describe. So G2 is also well known as the automorphism group of the octonions. It is a subgroup of SO7, and the embedding of G2 into SO7 gives another famous homogeneous space SO7 mod G2, and it has G2 holonomy. But it doesn't have SO7 symmetry. It's a squashed 7 sphere. I am not going to get into that, but it is related to some of the structures we're talking about here.
Sorry, is there a quick explanation for what squashed means?
Squashed means that a squashed sphere would look something like an ellipsoid. It means that it doesn't have a constant curvature space. It's got more structure.
Okay. Sorry, go on.
Go ahead, yeah.
Oh, I was going to move on to another question.
Yeah,
so if you had something else to say, please go ahead.
No, I don't. No, I don't. This is just an aside. This is
Okay.
a side throwaway mark. It's not essential to anything I'm saying.
Okay, so the other question I had was so how does this SO7 structure, how does it help you with the with characterizing these three?
Yeah, that's really what I wanted to go on to next. Right.
Okay. Okay.
So it's useful to think, at least for me, it's useful to think of G2 and SO7 together, right? Because again, we wanted to start with the 7 of SO7 and the 7 of or the 7 of G2, but the 7 of G2 is also the 7 of SO7 in a natural sense. Then that SO7 does have a 7-dimensional representation. It has this vector representation, and the tensor product of two 7s of SO7, right? 7 by 7, it breaks up as 1. The 21-dimensional representation, the adjoint of SO7 is 21-dimensional, and 27 is the symmetric tensor representation of SO7. So this base 7 times 7 is a nice, it's part of a nice family. And Brian Dolan and I, some years ago, we constructed a family with Peter Schneider. We constructed a family of quadrics. And this forms one of them. It would be called Q5 in that notation. And there's a fuzzy version of that. But so this one here, we can make a nice fuzzy version of this space because we can symmetrize the 7 by 7s and the symmetric product of 7s, which I mentioned earlier in the Dinkin labels here, that the N0 was symmetrized version of the 7, and it has a Fock space construction. If you're familiar with the Fock space construction of representations of SU2 in terms of A dagger sigma A dagger sigma A over 2A, in a Fock space, you get the representation. You can do exactly the same for the taking this T's and the 7-dimensional representation and working with Fock space. I won't describe that in DA, but that allows one to give a fuzzy representation of G2 of an SO7 space. But that space also has a G2 structure because G2 sits in SO7. This is actually very similar construction to the way that spin 5 sits in spin 6, which is SU4, and spin 5 is playing the role. G2 is playing the role of spin 5. SO7 is playing the role of SU4, and we expect to see something very similar. And in fact, we do. So what happens in that previous example that I described for you in terms of the gamma matrices, the 7 is like our gamma matrices of spin 5, and the 14 are like the generators of spin 5. But now we have a 7 of G2 and an adjoint of G2, and they together form a bigger group, which is SO7. So the analogy is quite strong. I've written out the generators. I'm not sure it's particularly useful but it gives you some idea of I've written out the 7 matrices of X7, which are the matrices of SO7 that are not the generators of G2. And this is a 7-dimensional representation, which is acted on by G2 by a joint action. And these 7 this is the representation out there. They have to look like generators of SO7, linear combinations of generators of SO7. Generators of SO7 would be ones and minus ones. It'd be natural to take a 1 and a minus 1 in all possible positions. So this would be a sum of 3 of those generators. This would be a sum of a different 3, and yet a different 3 here. Each of these are sums of 3 generators of SO7 in a natural sense. And the cartan, just in the basis that I'm using, I've written out the cartan of G2. The cartan of G2, well, this is T3, which has got zeros here. You can see there's a 3 by 3 matrix of zeros and a 4 by 4 matrix of zeros. And T8 splits again this into, it preserves this 4 by 4 and it splits the 3 by 3 by having another generator in there. And you can easily check that these commute, and they commute with, and there they form the cartan of G2. But let's focus first of all on the X's. These are the 7 generators of SO7 that form the part of the antisymmetric matrix, 7 by 7 matrices. All antisymmetric 7 by 7 matrices are the generators of SO7. So that's another reason to consider them. We're interested in the 7-dimensional representation. So we take the commutator of them. Well, they will close back on the generators of G2 and back on the X's. The anti-commutator of these ones, I've written it as a sum of these ones here. That's just an easy way of picturing it. But it decomposes into, the anti-commutator decomposes into the 7 and the 27 because it's symmetric. If we project out the 27-dimensional representation and just project back onto the 7-dimensional representation, so we project out this T, we get something that, a commutator of the X's, which gives us back to the X's. So projecting the X's back onto the X's and projecting the symmetrized one, we get that the symmetrized X's be 0. And we can take the square of them, of the X's, they go to the identity with this additional part. This is the part that is due to the 27. If we project it out, we get the projected version of the X's sitting after multiplying the X's gives us the identity, minus 6/7 times the identity. And the projection then of the product, when we project out these ones, we get these minus 6/7 times the identity, these C's times that. These C's are in fact the structure constants of the pure imaginary octonions. So what we have is, if we, and just I've given the convention that we've chosen here,Cijk is epsilon, ijk is completely, if I bring it as a completely anti-symmetric one, I take an ijk with being 1, 2, 3, etc. They give the value 1, and you can get the others from that. And the xj, as I've written them, are the components of these structure constants. So these are the structure constants of the pure imaginary octonions. So this is where the octonions are entering into the picture. The algebra of the octonions is obtained by this straightforward matrix multiplication of the x's, followed by the projection onto the identity plus the 7. We can then understand that the non-associativity of the octonions in this construction arises from the projection. Multiplication followed by a projection is not associative. So yeah, that's the essential point I wanted to make here. with regard to that. Now, the generator T8 commutes. This is the commuting set for T8, and it generates SU2 cross U1, these 4 generators. So we can denote the orbit of T8 if we take G minus 1 T8G with G an element of SU2. It gives us this orbit G2 quotiented by U2 minus, because it's leaving where U2 minus is this stability group. This adjoint orbit, it's related to the regular embedding of SU3 into G2. SU3, if I take the 8 generators of SU3, they will live in a 3-dimensional subspace of it, and we can take, or sorry, the eight generators of SU2 are T1 up to T8, in fact, and we can see that if we just take, if we consider one point on the orbit, you can see that I'm thinking now in terms of taking sigma 3 for SU2, taking the orbit under SU2, rotating it, you will get this, you will have a U1 that doesn't move the point, and SU2 orbited around that is giving us a 2-sphere. The 10 generators of G2 that do not commute with this one, there are 10 dimensions. They're going to span the space G2 quotiented by U2 minus at the North Pole. And if you track it down, you can see that the G2 quotiented by SU3 is S6. This is a well-known fact, but you can, and it's related to the X's that I had there, giving that something that looks like a 6-sphere. And this is the reduction of G2 mod U2 under U2 minus goes embedded in SU3. So G2 quotiented by U2 minus is a fiber bundle over G2 quotiented by SU2. And so what it has is it has a squashed, not a round sphere. This sphere, S6, is not round with a 4-dimensional fiber. Again, if you think about it a little bit, the adjoint representation of SU2 is the T8. So, and we are taking an orbit of T8 with SU2, with SU3. So if we take just one point of SU, if we don't move the SU3, we are generating the base space. If we move the SU3, we are generating an orbit fixed at the North Pole. We will get SU3 as the CP2 as the orbit of T8. So if I take, and it has these as the 4 tangent vectors at the North Pole. To summarize, just summarize that, the structure of this space is G2 quotiented with U2 minus, which is this Q5, and Q5 is SO7 quotiented by SO5 cross SO2. It's a quadric, and you can see that the structure of this is as a base space S6 with a CP2 as a fiber. And this is very similar to the CP3 example. One can squash, again, put a different radius because of G2. One can put a different radius on the CP2 to the S6, so that you make it a very small space, and this as a nice non-round S6 as your base.
Was going back to your other slide, yeah. Was SU3 the only option in order to break that down into a fiber bundle, or was there?
It was the only option for this construction. Okay. If I take an orbit of T8, I have different possible orbits. I have an orbit of T8 and I have an orbit of T3. If I take the orbit of T3, I get a different space. If I take the orbit of T8, those are the two Casimirs. So if I take this orbit of T8, I get one construction because T8, if you look at it, I should have probably gathered it again here. Oh, where did I?
Okay, I think
if you look at T8,
yeah.
T3 has a larger structure here. This T8 has a part here and down here, and it's again just breaking up the thing under how SU3 is embedded in it. T1 to T8 generate SU3 in this construction or in this representation. Okay.
And
yeah, please.
Okay, yeah. So the other question I had is, what is this Q5? Can you tell us a little bit about what
Q5 is an SO7 adjoint orbit. So I begin with the 7 of SO7.
Yeah.
And I take a particular linear combination of SO7. It has all of these cartan, or it has ones and minus ones everywhere in it. But if I take just the generator 1 and minus 1 here, for instance, of SO7, every place else is 0. That is left invariant by an SO2 in this two-dimensional subspace and an SO5 in this space here. So the orbit is that is a generator of a single generator of SO7, a single elementary generator such as R12. 1, 2 would be in a 1 and a minus 1 here. Then that orbit gives a space which is SO5 quotiented by SO7 quotiented by SO5 cross SO2. The SO5 from this block, the SO2 from this block, and the orbit in an analogy with this construction here, G of R12 G, where G is an element of SO7, gives you an adjoint orbit of SO7, which is Q5. Okay. That's this Q5. It is, in fact, the same space geometrically or topologically as this space here. But this one doesn't have the same geometry because the group that's doing it is G2. However, its structure here, we see by using G2, we can understand the structure of this space better, that it's a CP2 bundle over S6. And that comes out by just thinking about what is left invariant, moving with around with the two groups that are at my disposal, SU3 and U2 minus. So and just thinking a little bit about it and looking at the form of the matrices, it helps in that regard.
Okay. I saw at some point, just in passing, that Q5 might have something to do with assuming I guess octonionic triality. Do you know anything about that?
The octonionic triality is associated with SO8, if I remember correctly.
Sure. I saw just a lines somewhere that Q5 though is somehow related to triality, but
I would say it is really. I would say it is related to it, and in a sense, that's what's going on here. It's the sevens of if you embed this in SO8, yeah, and you use, I think it's described in some lectures of Baez around 2001, where he describes that triality and how G2 and is related to that, and SO7 fit in there. But it's essentially this construction. You're right, and the point here is really that the octonions, you can think of the x's to all intents and purposes as fuzzy versions of your octonions.
Right.
And if I take some commutative limit of them, the projection, we are satisfying the algebra of them when we project. And if I take multiplication of my x's and their generalization, there's a generalization which will again preserve this type of structure. And I was going to get onto that part of it, but these ones, the projection is in this way. I think it's the projection that gives you the non-associativity of the octonions.
Okay.
Anyway, okay. So this is the space Q5, but you can think of Q5 as this space as well. G2 quotiented by U2 minus. And this is, which is a CP2 bundle over S6, and S6 being G2 quotiented by SU3. There's a nice projector that goes with this, and the advantage of using projectors is that one can extract the commutative geometry of it, and you can see in more detail how this one is a projector associated with SO7 as well. So this projector, the orbit of this projector, if I take these ones here, this object here, I get a projector, and the orbit of that projector is precisely this Q5, which is the same one that I've described. The essential part that's happening here is that it's the orbit of T8. That's the essential part of it. And P1 commutes with those four generators, but it's not a linear combination of those. The metric and Kähler structure is encoded in this projector. If you introduce coordinates, you can extract that. And the projector associated with P5 can be written in terms of a symmetric matrix and an antisymmetric matrix, where M is minus n squared and n cubed is minus n. And n provides the functions. All functions on Q5 can then be represented in terms of n. And n is the 21 of SO7. And the functions in terms with these relations, all functions, just taking products of functions of the n's in a very similar way to the way you take products of x's to get YLMs, will give you all the spherical harmonics on Q5, and you can induce all the functions on this quotient space G2 quotiented by U2 minus. Just to show you how the thing goes a little bit further, I've decomposed G2 and the 7 of G2 under SU3, and you can see that it's a sum of a tree and a tree bar. And if you decompose it further under U2 minus, you have a singlet under U2 minus, and these additional ones. But the presence of a singlet was essential to get it as a nice to argue that it is the cojoint orbit and that this is the starting one. If I take the symmetric version of those, the next one up is the 27, and in general, if I take the N0 one, I get an object of this dimension here. So the size of the matrices that will approximate this space are dn0 times dn0. And if you count this 1, 2, 3, 4, 5, you will see that dn0 squared scales as n to the power of 10, which shows that by Weil's law, it's approximating a 10-dimensional space. So these are the family of representations that give you the complete fuzzy versions in analogy with the higher dimensional representations of that SU of the two-sphere. So that's the family of representations. The Laplacian on this d-dimensional representation is going to be I can take minus del squared as being 1/4 of the double commutator again, where TA is this dn0 rep of G2, and the eigenvalues, you can read them off, and they correspond to the functions on this space, just as you would expect. If you look at the next one up, as I said, was from the 7, you get 27 by 27 dimensional representations. Well, you see, if you look at it, this one here had 1 to 7, 14, 27. Well, and the next one up, you get 2 copies of the 27, but you get all of the previous ones. So it's just a cutoff version. This is a cutoff version of this. New representations are added. And if I go to 2, 3, etc., you can easily check that you get more and more of the representations. And it continues off until a high cutoff where we're associated with if we do up to n. And the scaling, as I said, goes like n to the 10, agreeing with Weil's law. And I think I've probably explained enough on that one, and I've even exceeded my time. So thank you very much for your attention. And let me go to questions.
Thank you, Denjoe. Does anybody have a question? I've got
there's a Hillary.
I think it's an
Oh, it's an
applause. Yeah. Okay. So is this generally a feature that the Laplacian is going to be the double commutator with the generators?
This is what you expect. In non-commutative geometry, you would expect that the generator would be the direct operator would be a first-order commutator, and that the Laplacian would be a second-order commutator.
Okay, got it.
So to get a second derivative, you should take 2 commutators. A commutator obeys Leibniz rule.
Yes.
So the first-order derivative will look like a commutator, and a second-order derivative will look like a double commutator. So you expect a double commutator.
Sure. Thanks. Okay, so Tavian's got a question.
So mine is perhaps quite elementary, but I don't think I had appreciated before the role and the importance of the complement of the adjoint, there's 27 here, in the representations of, in this case, SO7. Is there anything further you wish to say, or you could say, about the role that this, to me, unexpectedly important representation plays? The seven-dimensional representation has an algebra that has 49 components. So I need 49 matrices to span it. That's what you're referring to. And the 21 of those are the generators of SO7. The 27, so it's the 27 you're asking about. Yes, I can do the arithmetic. I'm just surprised to see it show up.
It is if you did the same construction, and I probably, I could have gone through it, maybe really more instructive than taking the 2-dimensional example for the fuzzy sphere. If I began with the 3-dimensional representation, the adjoint representation of SO3 for the fuzzy sphere, that has 9 matrices, right? So 3 of those are the adjoint. So the full algebra has 9 matrices. 1 is the identity, 3 are the adjoint, and we have 5 which are left over. Those are the symmetric matrices. So the anti-symmetric matrices are the generators of SO3. The 5 are the symmetric matrices. then they are the anti-commutators of the generators of SO3. Yeah? It's exactly the same for all orthogonal groups.
Thank you.
Right. So the 27 are the anti-commutators
Yes.
in the joint representation. We are using the vector representation, I should say, in general.
Thank you. For some reason, I'd never thought to do it for SO7 before. Thank you.
Well, I'm not sure why you would. So,
So I've got another very quick question, but it's actually not meant. It's not something that
I'll
you
stop
brought up.
sharing so that I can see.
Okay. Fair.
Yeah.
Okay. So it wasn't something that you had actually mentioned in your talk, but it was a comment that you made in your paper that I was curious about. It was something that you said that Bal had emphasized, was that I think you make the comment that U2 is conformally compactified Minkowski space. And I was just wondering if you could elaborate on exactly what you mean by that. So I could see how a U2 would be, the Lie algebra would look like a 4-vector. And so I guess somehow exponentiating is.
Exactly.
Yeah, okay.
It's,
So
that's
exactly
that. And
about as far as I got with that. So I don't know if you could fill in the rest.
If you think of the Penrose diagram for conformally compactified Minkowski space, this causal diamond type structure, you will see that it maps exactly into U2. If you think about it, there's
U2 the group.
Yes, the exactly that's U2 the group, and there's an old construction of Ullmann's, which it goes back to. I can probably put the paper in the chat if I can think of it, if I can find it. Okay. Yeah, I found it. I do have it handy here. So I'll put it on share.
It's okay. Yeah, it's possible actually that the chat might be turned off as well too.
Oh, okay.
A bit funny here.
Well, I can share the paper with you probably.
Sure.
You can see what it's the easiest way of answering the question is. I should open it first. Okay. It has the merits of being a very short paper as well. Let me see if I can get it.
There we go.
Okay. Let me see if I. Yeah.
It's wild that you had that so quickly available. Okay, closure.
Oh, you should see my office, how organized it is.
I was looking at that.
Yeah, sure. Complete chaos, but so this is the paper of Ullmann's, the closure of Minkowski space.
Yes.
So this is a well-known construction of mapping Minkowski space to 2x2 matrices.
Right.
And if you then take the Cayley transform of H, it gives you U, and now you identify M bar, which is the closure of M, and with the manifold of all 2x2 unitary matrices. So there's your construction.
Okay.
And you can track down you can work through the details of it rather easily.
Okay.
To see that this is conformally compactified in Minkowski space.
Okay. Wonderful. Thank you.
And,
does anyone? Yep. Go ahead.
Yeah. So you see, it's 2 pages.
It's the perfect paper.
And he gives the metric on it as well.
Very good.
Okay.
Thank you.
And I think you have the reference here, Actipolonic, Actiphysical Polonic in 1963. and the closure of Minkowski space. And
Got it. Thank you. Does anybody else have any other questions? Okay. So then now might be a good time to close things off. So I want to say thank you so much to Denjoe for putting together this talk for us and giving our opening talk for this year. And thank you to everybody for showing up. So our next talk is scheduled for after Christmas on the 16th of January, 11 a.m. Berlin time. We have Shogo Tanimura from Nagoya University speaking for us about a paper he wrote on super selection. So thank you again, Denjoe, for such an interesting talk. And we're looking forward to seeing everybody again next time. Oh, actually,
thanks. John, was John Barrett, I think he had a question.
so I see, Francis has a question.
These are hands up, not hands up. These are okay.
Okay, no, so Francis looks like he has a question here. So go ahead, Francis.
Thank you, Professor.
Yeah.
I would like to know, you in your talk, you made mention of the Pauli matrices, and you linked your operators to that of the Pauli matrix, and you also talked about the gamma of the Dirac matrix. And we know that the Dirac matrix is linked to the electron in physics when we are looking up for the structure of the electron. But the Pauli matrices are also linked to the spins of particles. In mathematics, the spins of particles have been known to be 2 by 2 when it's a spin half for a spin half particle, and also when it has a higher quantum state for a spin 3/2, and so on. I wanted to ask if it is possible to extend the fuzzy spaces of what you have done for the octonions. Is it possible to extend the results to that of spin particles? And also, what is also the relationship between the spin of a particle and the spin of a group? That's the spin.
That's a hard question for me to answer, I think. The way I think about these things is in terms of field theory. And the spin 1/2 particle, like the electron, is described by a Dirac field. And the Dirac field describes the particle and its antiparticle. So any spin field would be described by some any field. The photon, for instance, is described by a vector field with a gauge invariance that removes its transverse or its longitudinal components. The graviton is described by a spin 2 field, which we think of as the metric. Those are the only elementary ones that we know of, and the graviton is described by by G mu nu, the metric. Again, with a gauge invariance that removes the longitudinal components and makes it transverse traceless. Perhaps the answer to your question lies in the work of Harold Steinecker. Harold has been looking at S4 and CP3 embedded in higher dimensional matrix models, but essentially S4, as I described it, as a subspace of CP3. And if you think of it that way, there are the S2 that's sitting there describes higher spin fields. And if you insist that it has some fermionic structure as well, then it describes all of the fields that you want to, and Harold wants to push that as an idea that comes from the IKKT model, where he wants to get gravity and with additional spin structure and additional spin fields. So perhaps that's perhaps the answer to your question lies there. I'm not sure how to answer it in any better way, and to be honest about it, because well, you're getting into physics, and experiment will presumably tell us eventually.
Okay. I actually asked that because of the octonions, because I noticed that the octonions have been much delved into, and the structure of the octonions is to seek the nature of the gauge theory or the standard model.
Yes, I mean the real expert on this is called Furey. So I was really just looking at some relatively elementary mathematics on these things, and the idea, really, the one that I pursued more is that geometry might be emergent in some structures like this, and one can see some of these models where something like that emerges.
Thank you very much.
But I would recommend looking at Harold Steineker's papers for one part of it, and discussing with Cohl Furey how the octonions fit in with the standard model, because she has made a lot of progress on that.
Okay, thank you. I will do that.
Thank you. I think John Barrett has a question here. Oh, I think I have to ask to unmute you, John. There we go.
Okay, right, you should be able to hear me. So Denjoe, you talked about this vibration with of CP3 with fiber CP1 down to
Yes.
S4. Also, there's the other one with the octonion with G2. Do you get a sort of fuzzy version of this vibration? And can you sort of recognize the fuzzy sphere as the fiber of a fuzzy vibration, or is that?
You get in the fuzzy sphere. Yeah, absolutely.
So what size fuzzy sphere do you get, or does that depend on the other things you pick?
You're talking about in the CP3 case. You get fuzzy spheres that match, the matrices that you get match the dimensions of the CP3. So CP3 begins with 4x4 matrices. The next one up are 10, I believe, 4 times 5 over 2. Yeah, 10. So you will get those representations, and you can see that they are fuzzy spheres.
I see. So you can't dial the size of your fuzzy sphere. It's sort of fixed for you once you've.
It's fixed by the sequence of representations that you get there, but you can dial it within that sequence.
Yeah.
But you don't get everyone. The real point is that the algebra mixes with the algebra of the S4. They're entangled. You can't separate them.
So it's not really a vibration in the classical sense. Is that the point?
It's not a vibration in the classical sense, in that if I project onto the base, I don't get a closed algebra.
Mm.
Yes, exactly. I mean, in that sense, it's not a vibration in the classical sense.
I see. Interesting.
But I do get, but the whole structure exists as a. I mean, if you. The star product of functions would be that. I mean, the nice way of thinking of it is that S4 has you can think of it a nice round S4, and the S4 is round. It's given by a unit vector for a unit S4. But there's another tensor that's necessary, and it's an antisymmetric 2 tensor, which would be the complex structure if you took it to be, if you just took the tangent plane. But the complex structure of C3 local to the North Pole or any point of S4 gives you an S2 bundle over S4, and that bundle is CP3.
So
and it's exactly the twistor one, and this is an alternative way of viewing the twistor one from from that point of view. It's exactly that.
Mm.
But those are the S2s of the twister. Those are the fuzzy version of twister space, if you wish.
Great, thanks.
Sure. And just the G2 version is just a bigger version of that with exactly the same type of complications.
Right, with CP2 fiber. Yeah.
Yeah, except that the S6 is not round.
Great.
Does anyone else have any other questions? Okay. Thanks again, Denjoe, for such a wonderful talk.
Well, thank you very much for staying to the bitter end. Thanks.
Very good. Well, thank you for staying to the bitter end.
Okay.
Yeah. Bye now.
Bye.
Good to see everybody.
Yeah, you too. Take care, John.